This is another example of how to find the frequency response of an LTI system given a difference equation. So this is going to apply the discrete time Fourier transform to difference equations. So given this difference equation, we're trying to find the frequency response and the impulse response. Let's do it. So the first thing I'm going to do is take the Fourier transform of both sides. Right? So I take the Fourier transform of both sides, and I'm notating that by this curly f, or the script f in the curly brackets. Right? Script f. My script f is terrible. My curly brackets are just a little bit better. But here we have it. Now, I need the Fourier transform of the left. How am I going to get that? Well, I need to apply the linearity property. Okay, that allows me to take the Fourier transform of each piece. So now I'll do script f on y of n. And it allows me to just move the constants out. So then I'll take the Fourier transform of y of n minus 1 plus 1/8 the Fourier transform of y of n minus 2 equals 2 times the Fourier transform of x of n. So that's all the linearity property there. Take it piece by piece, move the constants out. Now, let's assume that xn has the Fourier transform, capital X, and y of n has the Fourier transform, capital Y. Okay? With that assumption, now we're going to start taking the Fourier transforms of these guys. So the Fourier transform of y is just y, right? Capital Y. Oh, that was easy. Now, 3/4 times the Fourier transform of y of n minus 1. So what does shifting by 1 unit do in frequency? Well, we need the timeshift property there. The timeshift property says that I take my Fourier transform, right, y, and I multiply it by a phasor, e to the minus j omega times whatever the delay is, 1. So we change the phase and frequency when we shift in time. Plus 1/8. Okay, here's the timeshift property again. So take my Fourier transform, capital Y, and then multiply by the delay, e to the minus j omega times the delay. So there's a delay of 2 there. So I'm going to write e to the minus 2 j omega, like that, equals 2 times capital X. Right? Okay, now on the left, I have capital Y common to each of those terms. So then I'll collect all of them. So I've got 1 minus 3/4 e to the minus j omega plus 1/8 e to the minus 2 j omega equals 2x. Okay, so now we need to use the convolution property. So if I have x of n going into an LTI system whose impulse response is h of n, I know that I get out x convolved with h. And so the convolution property says that convolution in time is multiplication in frequency. So I have that the y spectrum is x times the frequency response. So this was the convolution property. Convolution property. Okay, so in other words, h is y over x, right? Okay, so now I find y over x, so I divide by x, that leaves me with 2, and then I divide by this thing in brackets, and I find that capital H is equal to 2 over 1 minus 3/4 e to the minus j omega plus 1/8 e to the minus 2 j omega. So now the question is, how are we going to, well, that's the frequency response, really. So I mean, that's part of our answer, right? And so the question now is, how am I going to get the impulse response? I need to find the inverse transform of this thing. So how do I do that? Well, we can use partial fraction expansion. So let us try to factor the denominator. If the math gods have allowed for it, we can hopefully factor this thing. Let's think about how you factor polynomials. And I'm going to claim this is the way you factor it. Now, how did I get that? Well, as we've been saying all along, the omega is peanut butter, j is jelly, e is bread. So we look at e to the j omega as being the variable, and to get to collectively the variable. And in addition, we have the minus coming up with it as well, e to the minus j omega. So one could look at the denominator as like 1 minus 3/4, x plus 1/8 x squared, right? Because when you square e to the minus j omega, because of properties of exponents, then that becomes e to the minus 2 j omega, right? And so if you want to think of e to the minus j omega as being the variable x, this is what we have. And so how do you factor that? Well, you factor that as 1 minus 1/2 x times 1 minus 1/4 x, like this, right? And so you can check that if you FOIL it out, 1 and then 1/4 x and 1/2 x makes 3/4 x, and negative 1/2 times negative 1/4 makes positive 1/8. And so then this is the way that it's factored. But the key is recognizing that this thing, e to the minus 2 j omega, is the square of this thing, e to the minus j omega. Once you're comfortable with that, then we've factored the denominator. So now we need to write this as a over 1 minus 1/2 e to the minus j omega plus b over 1 minus 1/4 e to the minus j omega. So this is partial fraction expansion, right? And it's going from the common denominator back to the original fractions that made the common denominator. So usually we go the other way when you get a common denominator and you combine and you go this way. But using partial fraction expansion, we want to go this way because we know from common Fourier transform pairs, we know what the Fourier transform or the inverse Fourier transform would be of this thing, and we know what it would be of this thing. So let's find those factors a and b. So I don't care how you do partial fraction expansion as long as you do it correctly. My way usually is different than students' ways, and I will just try to maybe persuade you to use my way because it's faster and it can be done in your head. Trust me, because I'm very slow in math. I was actually kicked off of the math team in high school because I was too slow. So use that as motivation. But I'm going to show my work here, and I'm going to take it slow, and then we'll get B faster. So to get A, I'm going to multiply everything in that box by A's denominator. Okay, so let's do that first. So when I do that, on the left, I will have a term that cancels. Okay, and then on the right, I'll have A, which is good, plus B times A's denominator, right? Because we're multiplying everything by A's denominator. And then, this is an equation in e to the minus j omega. So this equation must hold for all values of omega. So I'm going to choose strategically a value of e to the minus j omega. I'm going to choose whatever made A's denominator 0, in this case 2. So I'm going to let e to the minus j omega be 2. And what happens here is, notice b gets multiplied by 0 because e to the minus j omega is 2, 1/2. So this is all 0, and the denominator is non-zero. So I have b times 0 over a non-zero, which is 0. So then I'm left with a equals 2 over 1 minus 1/4 times 2. 1/4 times 2 is 1/2. Right, so this is 2 over 1/2, which is 4. Right? So to summarize, I multiplied by a's denominator, and I set e to the minus j omega to be whatever makes a's denominator equal to 0. I bet you can do this in your head with a little bit of practice, and I'm going to try to do b in my head here. So imagine multiplying the full equation by b's denominator, so that you'll have a term that cancels, and then plugging in e to the minus j omega equals 4, because then you'll have 1 minus 1 is 0. That's what makes b's denominator equal to 0. So what I get is then b is equal to 2 over 1 minus 1/2 times 4, right? So this is 2 over negative 1, right? Because 1/2 of 4 is 2, 1 minus 2, and so this turns out to be negative 2 there, it looks like. So that wasn't bad, right? And so now we can come up to, I'm running out of room, so I'm just going to overwrite this. A, B. So we said that A is 4, B is minus 2. So what is the inverse transform to that? That's the impulse response. So this is from the linearity property. I can take each one of these separately and forget about the constant or tack it on at the end 4 times. Then the inverse transform of this guy. So from our table, I'm going to make some room here, of common Fourier transform pairs, there's alpha to the n u of n has a Fourier transform 1 over 1 minus alpha e to the minus j omega. So I look at that and I say, okay, well, I've got 4 times 1 over 1 minus 1/2 e to the minus j omega. So I form fit that, and I see that alpha is 1/2. So this is 1/2 to the n u of n, then minus 2, right? Linearity allows me to then consider this piece, minus 2 times 1 over 1 minus 1/4 e to the minus j omega. So I form fit this. I see alpha is 1/2. So this is, or excuse me, alpha is 1/4. So this is 1/4 to the n u of n. And that's my answer. If I like, I can factor out the unit step and maybe a 2, but that's it. That's the answer.